All right, Ruofan, please. So this is anyway, this is a work around the world.
Okay. Good afternoon, everyone. Today I will present the work AlphaGo. It's published in Nature 2016. There are two co-first authors. The first co-first author is from DeepMind, and he's also a professor in UCL. His research interest is AI, machine learning, reinforcement learning, planning, and computer games.
You can see, so this is a very typical example, right? The authors only have 5 publications, and now already, right?
The top 5 cited.
Okay, you can just look into the top 5. So how many papers has been published? But you can see his citations over 1 million, right? His citations over 1 million. Okay, the first few papers just taken. Okay, 20K. Okay. Okay, please.
And this is AlphaGo. And in next year, they publish AlphaZero. This is the second co-first author. His research interests are deep learning, reinforcement learning. He's also interested in tree search.
All right, so I just learned an anecdotal, right? So after the AlphaGo, so there have a lot of follow-up work like the Alpha Dota or Alpha Code, right? So which use the AI technique to beat the human in different field. Now the Ukraine war has started, and people saying that AlphaGo, the same idea of AlphaGo has applied on the war, and also on the United States military has also equipped the same ideas on the Air Force. So there's a news saying that the same line of technique has already beaten the top pilot in the army. All right, so I think that's very interesting to investigating those reinforcement approach. And I think that also very beneficial for our own research.
So in reinforcement learning, there are several basic concepts. The first one is the environment. Environment is just the game we are playing. And state is the current situation of the agent. For example, in Pac-Man game, the position of the Pac-Man is the state. And for action, at each state, there are several possible moves to take for the agent. For example, the Pac-Man can go up, down, left, or right. After taking an action A, the agent transits from S to a new state S prime.
In these games, the states is only the positions or also the situations of the enemies or the other kind of information?
I'm actually not sure because I think the position for the Pac-Man and the position for the ghost are, one is internal state, the other one is external state that is not determined by the agent.
So in formal like books and papers, the state includes everything. So information about the positions of the opposite agents or the positions of the food or the maze, everything.
Oh, okay.
So also as an undergraduate, so we actually did this project. I believe it's originated from MIT. So I actually did this, and I think apart from the position, we also, in order to achieve a higher winning rate, meaning taking the shortest time to eat all the food packages, we also need to consider the state of the ghost. Like you can see, if they are colored, it means they are not terrified, they are chasing us. But if they turn white, we can chase them. Yeah, so I think the state is a bit more complicated than the position. Also, the food packages are different as well. So if the food is larger, you can see the Pac-Man will be going after those larger food packages at the same position compared to if all the food packages are the smaller white particles. Yes.
Yeah, by the way, Zhang Yi is our new FYP student. Yeah.
Oh, hi everyone. Yeah, so just like to share, because yeah, we did this firsthand.
Yeah, that's really appreciable.
Sorry, Rohan, please continue. Yeah, thank you.
Ruofan,
Uh,
hello, please go on.
Now, in some of the games, the agent will receive an immediate reward after taking action. So for example, if the Pac-Man eats a dot, then the score will be increasing. If he missed the goals, then the score can be decreasing.
All right.
And policy. So policy is a function that recommends an action, or it gives the probability of actions given a state. And Q function is the utility of taking action A at state S. When we take action A, we may transit to different state S prime, so there's an expected sum. And the Q function includes two things. First is the immediate reward, and it also includes the future rewards from S prime onwards. Value is the utility when taking the optimal policy.
All right. So, so for this equation, so both are the scalar value, right? So, all right. So, any question here? So the R functions we're taking, S prime is the previous state.
S is the previous state.
S prime is the future state.
Yeah.
Or the next state if we take an action A. All right. All right, please. Oh, any questions here? I think some of us were familiar with reinforcement learning. Since Zhang Yi has already taken the courses, you can complement if we miss any things. And if someone who are not that familiar with reinforcement learning, don't feel shy. Just to raise your questions, interrupt us. That'll be totally fine.
Okay. So I think one thing worth noting is a coefficient gamma here. So maybe I can, I'm not sure. So please correct me if I'm wrong. So I'm also trying to refresh my memory. So as we can see, so this coefficient will determine the division of weightage that we put on the immediate rewards versus the future rewards. So during our experimentations, we actually caught this thing like how risky or risk-taking the agent will be. The more gamma, the larger gamma is, the more the Pac-Man or the agent will be chasing for future rewards. Whereas we can call this big R, I think, kind of memory of the past experiences. So this is like what he has been through so far, and whereas this is how risk he will be in chasing a future reward. So yeah, I think it's also interesting to experiment.
So in experiment, the gamma make a difference. So yeah. But for the immediate reward and the future reward, they're all learnable parameters, right? They're all learnable functions.
Yeah.
And how do you make a difference? And is there any conflicts between the immediate reward and future reward?
I think so. For example, if the Pac-Man game, if the Pac-Man is in a state whereas there's a big food particle just over here, but it had also ghosts chasing him, whether to eat or to flee at this point of time will be depending how we define the immediate reward and future reward functions,
and how the model will know the difference, and how we know that there's someone is coming for me, so this is more immediate reward, and how should I know that if we want to avoid the chase, it will be a long-term reward?
Yeah, so that is I think the core part, which what we call as a feature extractor. So given, for example, given this on this state, the feature extractor function will calculate, for example, if there's a ghost within this immediate square of the 9 points, then it will give a -2. And if the ghosts are in the like outer
so you are using different features represents different
yes, and we will
types of reward.
All these points up to evaluate the current state.
All right, so maybe how much you know about AlphaGo or the games of Go?
I'm not sure about AlphaGo's code, but I think if it's related to queue function, then maybe the feature extraction will be, of course, it will be much more complicated. So for the AlphaGo case, not sure, but for the Pangman case,
Yeah. By the way, how many of us has now the games of Go here? So I'm not saying the reinforcement learning on Go. I'm not saying that you manually play the game to Go. Anyone will played it before? Changshan, have you played it before? Changshan is not here, right? Anyone? Yufan, have you played it before? Hello, Yufan.
No, I didn't play it.
All right, so I stop asking. So feel free to interrupt us. Okay. Yeah, Ruofan, please move on.
So one
Okay.
more important point is here is that rewards are additive here, and for the reason we are giving.
Oh, sorry.
So the rewards are additive. So we just add the rewards from different states, right? For example, we don't multiply them or we don't use the different combinations. So that gamma coefficient makes immediate rewards more attractive than the future rewards, as one of the colleagues said. So.
But based on the formula, the immediate reward is a must, but the future reward is optional, right? Okay.
So we want to learn the optimal policy to maximize the utility. And to find the optimal policy, we basically want to find the optimal path. So we start from the root state S. Then there are a large number of legal moves. So we transit to new state S prime. Each move will lead to a new state S prime. And we keep expanding the tree until we reach the game length.
Okay, I have no question here.
So the optimal path is one of it. And the computational complexity is
So is this a question or?
it's a question.
Okay, so maybe you can clarify the question. So given a computational tree, right? So the game depth is D and the game breadth is B. And what is computational complexity?
To find the best path.
Okay, so anyone is volunteer to calculate this one?
Well, it was some exponential identity, like,
yeah.
But I don't exactly remember the identity itself. So
maybe you can write down the formula, and no matter, it doesn't matter whether it is a final outcome.
Well, yeah, on one hand, like on depth.
So you need to accumulatively calculate the sigma, right? To calculate the sums of the exponential.
Well, yeah, obviously the computational complexity is like b to the power of d, as somebody wrote. I haven't seen it, but yeah.
Oh yes, exactly. Is b to the power of d.
Okay.
So for the game of Go, because both b and d are large, so that makes exhaustive search infeasible.
Ruofan, so can you explain a bit why the B is 100 or 250 and the depth is 100 150?
I don't know.
You don't know, so you don't look into the rule of the games Go.
I think it's one is the number of board position, the other one is the game length.
So it means that for the games Go, it usually takes 150 moves to finish the game.
Yes.
And the search space for, but as far as I know, so there's 360, around 300, over 300, less than 400 positions. I mean, the position is about the cross point on the board. So I just feel the number of 250 seems a little bit, the number is more than I expected.
Hmm.
But anyway, so the point here is that the search space is huge, right?
So here are the two major contributions for AlphaGo to solve the first challenge, which is that the game length is large. AlphaGo tries to use a value network to predict the value instead of explicitly computing it. And to solve the second problem, they use multi-color tree search algorithm. Basically, it samples several different paths and finally choose the path that is mostly visited without going through all the possible paths.
Oh, sorry, can you repeat what is the multi-color tree search?
It samples several paths instead
Okay.
of going through all of them and find the best one.
Okay. Thank you.
So here comes to the approach part. The first stage is to train a supervised learning policy network. The input is the state. State is the board position. They encode the board position as a 19 by 19 image and feed them into a simple CNN network to get some kind of representation feature map. And the feature map is 19 times 19 times 48. The output is a softmax vector of action given that state. Training data are the human experts games. And training loss is the classification loss.
So here, what is the label? The label is okay. The human expert game. So so let me repeat here. So given a situation, so let me introduce the terminology of the situation. The situation is about the positions on the board, right? So given a position, given a situations, and it is basically a classification as which move I'm going to take. So so how many so which is classification problem. So how many classes are there in a situation for a situation?
Right? I don't know.
My question is the number of classes dynamic from game to games, or it is I think there must be a way to encode the next move in a constant number of classes.
Yeah. It should be fixed.
And how are they going to do that?
Because here you can see on the board there are different positions, so the number of positions are limited.
But right, they can encode everything, right? So they have there has on over 360 positions, and each positions can be filled into something, right? Put into a storm there. So there must be a way to encode it in a fixed number of classes. So this is basically a policy network, right? So I assume there are hundreds of classes in this supervised network. And what is mode architecture? Hello.
I need to check the
paper. Yeah. Okay, so if you don't know this idea, we can just move on.
But it's subjected to limited data. And also our goal is to surpass human experts. So they introduce another policy network that is built upon the supervised version, which is initialized from the first network, but the training data is the current policy network and is played against a randomly selected previous iteration of the policy network. And then we get the outcome Z. Z is equal to 1 if finally we win. It is equal to -1 if the opponent wins. And the training gradient is the classification gradient times Z. The idea is that if this time the current policy network wins, then I know that I'm moving in the right direction. On the other hand, if the opponent wins, then I need to adjust the network in the reverse direction to recommend some other actions.
Yeah, I think that's smart. So because giving the training data, we don't know. Anyway, so if we just learning how the experts played, but expert were beaten from time to time, right? So that must be there is a way to check the runtime to see whether this move, despite it looks like some experts move, whether they can bring me the good benefits. But anyway, this we haven't touched the reinforcement learning part. It's just about the classification network, to train a classification network, right?
But they call it reinforcement learning policy network.
I understand. So this network just actually a simulation. So more like evaluation. So given the situations, we still want to see which actions will brings me more benefits.
So it's like a data augmentation via self-play data. So that's for the reinforcement learning part.
All right.
And the third network is called a value network.
This third network, I assume that the first and the second is actually the improvement of the first, right?
Yes.
So I mean, we either using the first or the second network in at the runtime.
We use the first network.
Yeah, we're using the first network, but so we'll go back to the previous slide. And the previous one, and the previous one. And here you're saying that this okay. So this RL policy network is initialized from 0. I think the first and the bullet, the first bullet and the second bullet are the network share the same functionality.
Yes, but in their
Right.
experiment, they find that the first one actually performs better than the second, but the RL policy network helps to train the value network.
I see. So RL policy network is more like in the intermediate temporary network for. Yes. Okay, you can move on.
And for the value network, the input is still the state, and output is the outcome of the game. Ground truth value is -1 or 1, but the predicted value is a continuous value. And the training data is from our second network, reinforcement learning policy network. We have generated several self-play data. And the training loss is the regression loss, which is mean squared error. And in AlphaGo, the value is defined as the outcome of the game. So there is no intermediate rewards. We only care about the final outcome.
All right, I have no question here. Anyone have a question here? If no questions, let's move on.
So actually there are 4 networks. The first one is the supervised learning policy network, which maps from state to action and is trained with real games data. They also train a simpler version of supervised learning policy network. It's less accurate but faster. It is used in the later multi-color tree search algorithm.
This is the rollout policy you're highlighted.
Yes.
The question is that is from by comparing the SL, SL means the supervised learning, right? From the SL vs rollout policy, and the difference is just about the network architecture. So it seems it's more efficient. So which means that the rollout policies were used for, we have a requirement for it to be efficient, right?
Yes.
And its efficiency used for
multi-color tree search. Later I will introduce.
And the multi-color tree search. So here, which one is used for the intermediate training, and which one used for the runtime sampling?
They are. This one is This one is intermediate because it is used to train.
And
the
how about the rollout policy? I'm talking about the difference between
Oh.
the rollout and ACL policy.
This and the value network are used in the runtime search.
Which one and the value network for? So ACL policy and the value network.
SL policy.
We will only use these two network, and all the rest are just for intermediate training.
Only RL is for intermediate training.
And what about rollout policy? So which means that at the runtime we're using 3 networks.
Yeah, we're using 3 networks.
And the policy and I think the ACL policy and the rollout policies are used for the same functionality, and how the approach is switch between the rollout and the ACL policy.
Are used for different functionalities.
Or different functionalities, okay, but they share the same input and output.
Yes.
Okay, but you will introduce this later, how they're different.
Yes.
All right, so I keep my question here. You can move on.
And the RL policy network is trained with self-play data. The value network maps from state to value is trained with self-play data. And AlphaGo combines the policy and value network in a Monte Carlo tree search algorithm. The idea is that it simulates the game for many times from the root state, and each time it may go through different branches. The more simulations I have, the better my estimation of the optimal value is, because I look at more global picture of the full tree. And finally, the algorithm will choose the mostly visited move from the root position.
No question here. Yeah.
So at the T simulation, starting from the root state, an action is selected by maximizing.
The T simulations means the T scan for T simulated gains, right?
Yes, it's simulated.
Okay, it's not a move, it's scan.
Yeah.
Okay.
And here, this action is chosen from 2 different terms. The first is the Q function. Q function relates to the outcome of the game. So we try to select the action which maximizes the outcome. And the mu here actually encourages exploration. That means we visit the action that is not visited by the previous simulation.
And so it's quite straightforward to, you have explanation, right? So please go on. Okay.
So actually is proportional to the P divided by 1 plus N. This P is the output from the supervised learning policy network. So if the policy network recommends an action with higher probability, then the mu would be higher. And N is the number of visited times in previous simulations. And we try to explore new actions.
The question is there, what's the relation between P and Q?
There's only a relation between P and mu.
I understand that there's P and mu, but I think that I understand. So the more you visit the state, or the more you take an actions, and this action will be kind of discriminated, right? So, but the P is learned from the SL policy, and how is Q? And Q is still something from the value network, right?
And Q is something from the value network. And Q is actually an average estimation of value over all past simulations. And
by taking the action of A, right?
Oh, yes. And the value is actually a weighted average of 2 terms. First one is the predicted value from the value network. It can give an estimate of how good the state is. But they also take another term, which is the outcome when we play with the rollout policy network, because rollout policy network is faster. We use that action and
let me think about it. And would be okay, taking the Q and V. And so the Q function is taken from the both value network and the rollout policy network.
Yeah.
So is there a difference? So which means that the SL policy network and the rollout policy network share the same training data. Am I right or not?
Yes.
But it just want to be efficient.
Yes.
And also based on this formula, it means that the rollout policy network will still be used on runtime.
Yes.
Okay. So any question here, or John, you want to complement anything?
No, I actually I feel a bit lost because
Which part is lost? So I can try to explain a bit.
I'm not sure why we need to use an intermediate training network. So although I get it that
I think we haven't reached there.
Huh?
We haven't reached the intermediate network yet.
Intermediate network.
Yeah, we haven't reached there. It's just about the overall algorithm design. So this RL policy network has been discussed, right? So we're just talking about the route policies and SL policies and the value network, and we haven't touched the RL policy network.
Oh, we have already.
Oh, we have already passed which one? So sorry, I missed that.
Okay. I think the RL policy is just to generate more data by playing with itself.
All right. Okay, so that's a policy. So you will not introduce how we train the value network anymore. You will not introduce how we going to train the value network anymore. So that's all you're going to bring us.
Yes.
All right.
Because the value network just use the self-play data from the RL policy network.
So the only purpose of the reinforcement learning network is to provide training data for this value network, which we finally used.
Yes.
Oh, okay. I see. Actually, there are a few like details. I'm not sure, but I think I can find out. For example,
you get a big picture. I think you get a picture. I think the presentation here is that two goals. The first is that someone bring us the knowledges. It can save us a lot of time and effort to look into the papers or find the videos outside. I'm definitely sure there are other videos here, but anyway, someone brings here, and we have time to group all people here for discussion. And the second part is that we can have discussion. So someone is read the papers, someone read the original Nature paper, right? So it will have more detailed information, so we can interrupt and have an interaction and discussion. I think that is a very good opportunity. And also last time we introduced the first author of another paper. So comparing to the people who present the paper by their understanding, if we have a chance to invite the first author of the paper to introduce as a work, so that's also a very good opportunity. But I'm thinking about more how to organize these meetings in a better way. But let's keep move on.
Okay.
So maybe I will go through the multi-country search again with some visual aid. Here is our root state. And we will choose the one that maximizes the Q plus mu every time. And
we calculate the maximum.
Yeah, calculate the maximum. And because this mu depends on these two things. So if this branch has been visited previously, we may try to expand some new branches that we haven't seen before.
On the point, the question is here, how do we know this path has been explored before? So the games are very different, right? And there must be a simulation.
We know that we take different action. And one action is new.
And how do we know that we are within the same state? And how do they design this?
Because the state is just the position of the white chess and the position for the black chess.
You mean stone?
The
position in the white and black stone.
Yes.
The point is that they're so giving two board, right? Giving two board with black and white stones put on there. And if I change a very minor, we have a minor change. So I move the stone, one stone left or right, up and down, and whether they believe it is same state or not.
Different state.
totally different state. So in that case, the chances to visiting the same state will be small, right? So you can say there's 361 positions on the board, and each board will have 3 options: the black stone, white stones, and empty, right? So it is basically on an overestimation is 3 to the power of 361. So the chances of visiting the same state will be small.
If this term only depends on Q, then we will only visit one action. But since we add a mu, so we
there's a definitely at each state. If the state is board position or board situations, we have only, I think we still have a large number of actions, right? We can put all the stones on we're empty position there. But the case is that you're saying that we're visiting the same path. We have to calculate the n, right? NSA. So how they calculate the duplication?
NSA is just you count in the past how many times you go through this action.
How many times we go to this action?
In the past.
Actually a path consists of nodes and edges, right?
Yes.
And one node is a state, and one edge is an action, right?
Yes.
And so I'm asking, how do they calculate the consider the duplicated path? So state action, state action, state action. Suppose we have 5 nodes and 4 edges on the path. And how do we now so the question is exactly whether it is exact match or there's a tolerance of there's similarity threshold to tolerate a little bit different paths.
Well, this is just one action. Or it just counts for one edge.
Yes, so it is for one action, even if it is for that, but for the state number is supposed to be very large. And it's very hard for us to revisit exactly the same state, right? So because a minor change of the black and white stone, and it is supposed to be it is supposed to be a different stage, right? Different state.
I think from the illustration, it could be eliminated by considering only a portion of the whole playboard.
Yeah. So that's a justification or a medications. But I'm asking whether the authors or whether the paper have mentioned this.
No.
Okay. So if you don't have no idea, we can move on.
So the Q actually is an average estimation of the value. And the value depends on 2 things. So when we reach a state SL, we try to use the value network to predict the final outcome. We also use the rollout policy network to play the game, and then we reach an outcome. And we add these 2 things together.
All right. So any question here?
Sorry, this may be a stupid question, but I really want to ask. So how does the rollout policy network help in the playing or determining the action?
It's faster.
So maybe I just share my understanding. So the value network is just a way to evaluate the situation, right? So there's a main position of blacks and white stones on the board. So we just have estimation. But for the rollout policies, it will really to play with the games to get the real outcome. So more like a static dynamic functions. So the value network evaluated the static benefits or reward, and the policy network were actually, this is the uniform color sampling, right? To sample a few paths to interact with agent or interact with the environment to get the dynamic reward.
Okay, so the prediction will be like a continuous range from 0 to 1, whereas the rollout policy that will give us either 0 or 1.
I think they will give us still
Minus 1 to 1.
still give us continuous value.
This DL is either -1 or 1, but this value can be continuous.
Okay.
Okay, I see.
Yes.
Okay.
So which means that if we're going to get we want to get a ZL, we need to finish the whole game.
Yeah, we need to finish the whole game. That's why we need a faster network.
Okay.
Okay. But let's say the rollout policy give us a 1, which means it wins using the multi-color sampling search. Wouldn't that just outweigh the prediction from the value network?
I think it will update the value network, right? You can see. So the value of ZL will be one component of VSL. So I think it is a way to minimize actual reward and the estimated reward.
Okay, I see. Okay, yeah. Thank you, Ruofan.
So in practice, they take lambda to be 0.5. They find that performs better than either.
Lambda equal to 0.5. Okay. Okay, let's move on.
So in their backup step, they just update the QSA because now they have a current estimation of value.
Okay, the approach is over, right? So okay, so I think it's better to us to summarize a little bit, because Ruofan introduced into an abstract way, especially on some of us like Yufan do not have experience of games go. So in the questions for the whole approach, I think Ruofan clarified in an abstract view, but if any of you have any detailed questions about its implementation. All right, so if there's no questions, we can, please.
Yeah, I still feel a little bit lost related.
Hey, Dr. Xiang, have you played Games Go before?
No, but recently I indeed read some papers related to reinforcement learning, but it is much complex than that one. That's why
Why so simple, right? And it's in nature.
Yeah, so now it's very, I mean, this one is much complex. I mean,
which one is more complex? This one or this one?
Yeah. So I'm still a little bit lost. Could you please summary?
First, we have 4 networks. So we have 3 policy network. These 2 are trained with human experts game. The only difference between rollout policy and SL is that rollout has simpler model architecture. And RL policy network improves from the supervised learning one by using self-play data. Then value network is trained with the generated data from RL policy network. So this RL policy is only an intermediate network, but the rest 3 networks are used in the later multi-color search algorithm. For the multi-color search algorithm, we basically simulate different paths from the root state and to get a good estimate of what is the optimal path, and we choose the mostly visited move from the root position.
Okay, so maybe I can briefly complement a bit. So Ruofan, can you go back to the previous slide? Yeah, so I think the overall idea is that given a situation, given a board, right? Given a board, there are black and white stone layers, and the machine is going to pick which place or which position we're going to put a stone, right? So there's this action. So basically there will be a classification problem. Of course, the number of classes will be huge. So when we talk about this network, we may think a little bit about how we play the games. So we have a move, and our opponent will have another move and back and forth. So in this regard, we still have a search tree, right? So one move, another move, one move forward another. So there will be a search tree there. So the idea that how to reduce the search tree. In this case, we will have estimation. So the ultimate estimation. The approach to estimate these were to using a value network and a policy network. The value network is used to evaluate the situation. So in given the situations, suppose I take a move and the game will turn into another situation, and what is value or what is measurement? What is the measurements for me to know that this situation is benefit for me? And another way is that we use a policy network. So it's that, so if we want to simulate the games in the memories, we somehow need to estimate which action to take during our calculation. So that is a way of the rollout policy, right? So for us to simulate, and the value network and the rollout policy network, and to construct the value of Q function, right? So which means that Q functions will need to use the value network and the rollout policy network. And in contrast, there is a U function here. And this U function was just a way to balance the exploration and the exploitation. So the idea that using the SL policy network, which means that if we take certain actions, it will still benefit for me. But in the meantime, this path is supposed to be a path less explored. Right. So I think that's more of my understanding. Ruofan can correct me if I miss anything. Okay. So any question here? If no, let's move on.
So they have some evaluation for the individual network. You can see that for the rollout policy.
I cannot see your slides moving. Okay.
The
It's
rollout
moving.
policy, the accuracy is lower than the supervised learning policy, but it's much faster.
Oh, sorry. So what does the accuracy stand for? 50% of what?
It's the classification accuracy.
So like based on the final result.
The training accuracy.
The testing accuracy.
The testing accuracy. Okay.
Okay, I see.
So which means that it's not. It only the 50%, right? It just follow the 50% of the it's not that fitting to the training data.
Yes, but the state of the art is 44%.
I see.
Well, yeah.
So the state art is the state art at 2016, right?
And the evaluation for the RL policy network is when they play with the SL policy network, they can win more than 80% of the games. The evaluation for the value network is for the testing mean squared error. And they actually played against other open source Go program. They find that the best version, which is the distributed version of AlphaGo, was significantly stronger. It can win 77% of game against the single machine AlphaGo.
But in this paper, you haven't introduced any details or technical details of the distributed version.
Oh, so for the multi-color search algorithm, they need to search so they can like distribute their searching into multiple machines.
I see. So which means that more computation power, right?
Yeah, more computation power.
So if it's distributed, does it mean it can like sample more passes? Or
exactly. Yeah.
That, okay.
Exactly.
So we have learned the policy network, value network, and the multi-color tree search algorithm. That's the takeaway from this.
All right. Thanks, Ruofan, to abstract I think it's very quite a lot of details, right? So, but anyway, I think the overall picture and overall idea is quite straightforward. And for as far as now, the AlphaGo, the deep learning, the DeepMind company has announced that they will no longer maintain the AlphaGo project, right? Which means that they firmly believe there's no human beings going to beat AlphaZero for a long run. So anyway, I think the reinforcement learning is very, very popular and useful technique for us to investigate on the research. Maybe we will investigate the time in the reinforcement learning research, or maybe we using reinforcement learning as one of tool, which means that we need to understand the model design. Just like Dr. Xiaoyan mentioned that we're looking to manage design of reinforcement learning. And if we want to apply it into games to go, so we need to customize it a bit. But why we want to customize in this way? So I think this tricky part and it requires more domain knowledge. Yeah, so I think these are good presentations. It give us a hint maybe on it will be useful when we design our own approach on the reinforcement learning approach in our own work. And by the way, so Ruofan, please do share the slides. Any questions for the whole work, and any question we welcome. Don't be shy and don't worry if you ask some irrelevant questions. All the questions, as long as you ask the questions, it is relevant. All right. Maybe Ruofan, you can raise next presentation. I think we can raise more questions, not just one questions. We can raise maybe 3 questions, and for multiple of the participants to answer, right? Okay, I think if there's no questions, maybe I raise the question again. Is there any questions here? And the question can be relevant to the presentation or a little bit further away from the other stuff about group, because we have new people coming. And Zhang Yi is the one who raising the question, but they're also on Chen Hing, right?
Yes.
Any question there?
I'm okay now.
Okay, so if there are no questions, I think we can call it a day.